All right, everyone. I have some too. I just can't talk with them in my mouth. Yeah, thank you though. I know, but I'll wind up spitting it out. All right. So I don't have your exams. As I was telling a few other students, I got sick on Wednesday or Thursday, and I didn't actually even come to school after our classes. That was the last day I was here, and then so I didn't come on Thursday or Friday. I came back today, and my class earlier today, I didn't lecture. We did a review, so I haven't actually tried talking for a long period of time. But on Saturday, I couldn't talk. My voice was completely gone. So I don't know what I had. It wasn't strep. It wasn't the flu. It was just something. So I'm going to see how it goes up here. But if my voice starts to go, you know, I'll just kind of go like, all right. So a couple of things have been pointed out. Um, the homework assignments that are at the end of these notes, I did these notes back when we were using the first edition of the book, and so the page numbers aren't matching up, and I didn't realize that because I forgot about it. So it's been pointed out that all you have to do is if it's the notes for 11.6, then go to that section in your book and do those problems. Don't worry about the page number. Just do those problems, all right? What else? Oh, we have a mini exam that I'm going to hand out to you today. All right? So let me get this handed out. I hope you enjoyed a weekend of no work. If there are any extras, pass them down this way. Here you go. All right. Everyone have a copy there? Extras? Got it? Everyone has them? So if you look at this, let's just talk about this exam real quick. The first the first one you should be able to do now, because on part A, I ask you to find a couple of partials of a function. Part B, I ask you to show that a certain function satisfies the Laplace equation, which means you need to go back in the notes and remember what the Laplace equation was. And then the third one involved chain rule, which is what we ended with last time. And that means I would like for you to draw a tree and show me the branches and then come up with your computation. Man. All right, and then number 2, we're going to talk about number 2 today. All right, we'll be able to answer number 2 today. I don't think we're going to get to 3, but possibly. Number 3 is 11.7. And I hope to do 11.7 because the rest of it, number 4 is also 11.7. 5, 6, 7, and 8 are 11.8, which I said I didn't want to put on this exam. So let's just see how let's see how this week goes. Because we might actually get to 11.8. Yes. Let's just see, because the midterm's going to be, a week from this Thursday? We only have this week, and then next week, and then spring break. Wednesday. So it would be next Wednesday if we had the midterm. That's supposed to be due on Wednesday. Yes. But no, next Wednesday, right? Next Wednesday. The 5th. The 5th. So let's just see where things land. Let's see how today and Wednesday goes this week. I said 11.7. 11.7. That's what's on the schedule. What I'm telling you now is that we need to get through 11.8 for you to be able to do this. So what may wind up happening, I don't know yet, is the midterm may cover up through 11/7, but that take-home might be extended to after spring break, including 11/8. But I don't know. I want to see how we go here. All right. I don't want to ruin your spring break. Okay. So let's go ahead and get moving on this. Okay. We are going to talk about 11.6, which is called the directional derivative and the gradient vector. Some of you may have heard of the gradient before. So it really isn't that bad. First thing we're going to do is we're going to take a look at a surface. All right, I'm going to bring this file up here in just a second, and I want us to look at a few things on it. So let me grab this file. The file I'm opening is a file that I did not write the code for this, a little disclaimer, but I modified the code to do a couple of things that I wanted it to do. So just so we're all clear. I don't want to take credit, that's not mine. Okay, so what we have here, if everyone can see that okay, is a surface. Can you all see the surface all right? I can make it a little bit more solid. Does that help? Does that make any difference or a little bit better? Okay, so we have this surface, and then if we look at it from the top, straight on from the top, we have our x-axis kind of along the bottom, y-axis here, and then the surface comes out towards us in the z. And then the point on the surface has an x-coordinate, a y-coordinate, and then the z is how high that is, right? How far out it comes. Right? That's what we've looked at in the past. And then last class, or last few classes, we talked about the partial derivative. What the partial derivative was is we took this and we cut the surface with a plane that went parallel. You could say the plane would come straight down, cut it parallel to the x-axis, and that was our partial. That would be the partial with respect to y because you're holding x. With respect to x because you're holding y constant. And then if you cut it like this, straight down like that, then you're holding x constant. That would be the partial with respect to y. And when you do that, no matter which way you do it, this way, horizontally or vertically, the way we're looking at it right here, horizontally or vertically, you'll have a tangent line on that curve, right? And that's what the partial represented. Do I need to bring that picture back up? Do you remember it from last time? But what's to say we have to cut it with a plane that's parallel to the x-axis or y-axis? Why can't we cut it with any plane and then see about a tangent line? And that's what the directional derivative is about. It's about saying, hey, go to any point you want on the surface, and then so imagine I'm standing here on top of this surface, and let's say, my finger's pointing in the way I'm looking. Okay, so I'm looking that way. I can go in any direction and then say, okay, in that direction, what's the slope of the tangent line? That's directional derivative. So let me pop this back out like this. Now below the surface, do you see this dot? That dot is actually the x and y down on the ground. So that's the point on the x and y that gets plugged into, the function comes up. And I put a little arrow on it to show the direction I'm pointing in right now. So it's like the person standing up on top of that, and I'll bring him over that hill so you can see him a little better. Come here. There. Okay, so now he's standing there. Now that guy is pointed in the same direction as that red arrow. Following me? I will bring the surface out. I'm going to look at it from the top. Now what you'll notice is that even though my black dot is not right on top of the red dot, what I'm saying is that I'm pointing in the same direction as that red one. All right, now, here comes the plane. Let's cut this with a plane, and notice that that plane is pointing in the same direction as the red arrow, okay? And where that plane intersects the surface is a curve, and that curve should have a tangent line to it. So here's the tangent line. Ah, man. Bring it back around like that. Do y'all see it? Now, that looks like what plane did I cut it with there? That looks like a plane that's parallel to the XZ plane, doesn't it? See if this helps if I bring it darker. And no, that didn't really help. Okay, so yeah, now let me say, forget that. Let's just change my direction. So what I'm going to do is I'm going to grab this slider here, and I'm going to start changing my angle. Yes. No. No. The point. The red one is on the ground, and all it does is tells me what direction I'm pointing in. So when I looked at it from the top, notice that the red is parallel to the plane I'm cutting with. It's a direction, correct. It's actually a vector. It's going to be a vector to us, but I put a point on it. Okay, let's rotate. Let's rotate and see what happens here. I'm going to make this a little smaller. Okay, here's my little slider. So my angle, if this is X and this is Y, then what do you think the angle is right here, right now? What's the angle? 0, right? Because the x-axis was always 0 for us. So as I start increasing the angle, I should start rotating this way, right? Okay, let's do it. Oh. That's why I put this one in. Okay, so I can go to any angle I want there. And now, you see we're pointing in the same direction that plane is. When I come in this way, notice that the slope of this tangent line, doesn't that look different than the one we just had? And as I change that angle, that slope may change also. Whoa, jeez. And it really messes it up when I move things around. Am I making you dizzy? There we go. I wanted it over here. That. The red, you mean? All the red does is gives us the direction that the plane is running parallel to. That's all it does. So again, imagine you're standing on top of the surface, whatever it is, and every direction that you point, let's say this is 0, I can say rotate by 30 degrees. Okay, then start to walk. The slope of the tangent line in that direction is my rate of change in that direction. Right? If it's positive, then I may be going up, right? If it's negative, then I'll be going down. Make sense? If it's very positive, right, large positive number, that means it's very steep there. And if it's a large negative number, it's very steep going downward. Okay, so the direction, I'll understand the idea geometrically of what's happening. Okay. See if there's anything else I wanted to show you here. I can take the surface out completely. I can take the plane out completely. I like the plane. And I can just start moving the angle around. You can kind of see from this that changing the angle, you have a different curve in every direction. All right, let me get that out of here. Where's my other file? The angle relative to the x-axis. It's just the way I'm facing. That's all. The angle is just which way I'm facing. If I'm standing on the Earth somewhere, I'm on a surface, then if that's 0, then my angle is just this. Right? That's all it is. Okay, so we picked any point, right? We can pick any point in the domain to get a point on the surface. At that point on the surface, we can point in any direction. In that direction, there is a tangent line. The slope of the tangent line depends on what direction we point in. Okay? All right, now the definition of the directional derivative. If z equals f of xy, that's a surface, then f has a direction, we call it directional derivative, in the direction of the unit vector. That means that vector has a length of 1, okay? In the direction of the unit vector u, which is the vector AB, right, in our angle brackets, and the directional derivative. So remember what we did last time? if I wanted you to do a partial with respect to x, there was all these different notations for it. But here, d with a little u vector under it is basically the partial in the direction of u. That's what that's saying. Of f of xy equals, look at what this is. A f sub x of xy and plus b partial of f with respect to y. So isn't the directional derivative just a linear combination of the two partial derivatives? And think about it this way. What if I'm pointing out the x-axis? What if I'm looking out the x-axis like this? What is the direction vector? What's u? What's a unit vector pointing out the x-axis? Looking from the top. What is it? 1, 0, right? If I were looking, I've forgotten how all my little things work here. I'm going to come back here. I'm going to imagine this is looking from the top, okay? Remember I had that red dot? I said, let's point it this way. If I'm pointing it that way, what's a unit vector that points in that direction? That would be the vector 1, 0, wouldn't it? That'd be 1, 0. So my plane points that way. Well, what does this formula become if you replace a with 1 and b with 0? Partial with respect to x. And isn't pointing in that direction holding your y constant? And that's what the partial with respect to x meant. And then what if I change it and I do unit vector pointed in that direction? So that would be 0, 1. And all that would be the partial with respect to y. So do you see that the partial with respect to x and the partial with respect to y are just specific cases of the more general directional derivative? That's all it is. Got it? You have to have a unit vector for this formula to work. All right. Here's an example. If z equals f of xy, blah, 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 then find the directional derivative at the point 1, 2 in the direction of a vector making the angle pi over 6 with the x-axis. What? I'm sorry. If I annoy you, I just apologize. I've been annoying myself coughing so much. This video is going to suck if you ever have to watch it. Okay, so we're going to need some partials, right, for the formula? But let's start off with the u. We're going to need u, aren't we? The direction that we're pointing in. Well, all I give you is that the angle of u is pi over 6. Right? Can somebody tell me a unit vector that points in that direction? Root 3 over 2. And then this side would be 1/2. And that just comes off the unit circle, doesn't it? And so the vector u equals root 3 over 2, 1/2 will work, won't it? So in this, I gave you the angle. You have to convert that angle over to a vector. Now, out of curiosity, what would you have done had I given you an angle like pi over 8? You need a calculator. You need to set up your right triangle and try and find the sides using ratios and things like that. So I'm not going to mess with you like that, but I'm just saying, in this case, pi over 6 was nice, but in general, you should be able to do any angle. All right, so now we need some partials, right? I'll get to the formula in a second. Partial with respect to x is 3x squared minus 3y, and that's it, right? Partial with respect to y is negative 3x plus 8y. Hopefully you've done enough of your homework that you've got some practice with partials. You're comfortable with those? So now we go ahead and bring in the derivative, the directional derivative. Capital D subscript u of xy will be equal to, what is it? Root 3 over 2 times the partial with respect to x, which was 3x squared minus 3y. And then plus, right? 1/2 negative 3x plus 8y. And I want specifically the directional derivative where? At the point 1, 2. So now we say, okay, now that that's a formula for my directional derivative, I plug in 1, 2 for x and y and get some number. Let's see, plugging in 1, we get 3 minus, let's see, 2 there is 6, plus 1/2. Plug in 1 there, we get negative 3, 2 there, you get plus 16. So negative 3 root 3 over 2. And then, what's that other one? 13 halves, which is 13 minus 3 root 3 over 2. Now you could get that as a decimal, but you could also just leave it as an exact answer. My question to you now is, if that was you standing on that surface, pointing at pi over 6, and you took a step, are you going up or down? You're going up because that's a positive number, right? All right, that's it for that. All right, this problem is a little bit different. Uh-oh. If z equals f of xy equals natural log x squared plus y squared, then find the directional derivative at the point 2, 1 in the direction of the vector u equals negative 1, 2. Now, I am intentionally trying to trick you here because I've given you a direction vector, haven't I? I've called it u, but you can't use that. Why? It's not a unit vector. So you have to turn it into a unit vector first. So how do you find a unit vector? If someone gives you a vector and you want to find a unit vector pointed in the same direction, all you do is what? Divide by its own magnitude. So we're just going to scale this vector appropriately first, okay? And I'm not going to call it u, I'm going to call it v, just for the hell of it. So v equals, let's see, what is the magnitude of that vector? Square root of 5. So it would be negative 1, oh, jeez. Negative 1 over root 5, and then 2 over root 5. That's the vector you'll need. So that's really technically in the formula, that's the u, isn't it? But I'm going to have to write this out correctly. So I'm going to say directional derivative, and then what? Subscript. I'm going to use v to make my notation correct here. Equals, and then negative 1 over root 5. Oh, wow, I didn't get the derivatives. I jumped the gun here. But let's try and do the derivative mentally. What's the derivative of natural log of something? 1 over it, right? Times the derivative of what's inside with respect to x. What's the derivative of what's inside? 2x, right? So it should be 2x over x squared plus y squared. That's the partial with respect to x. And then I have plus 2 over root 5. And then what's the partial of f with respect to y? 2y over x squared plus y squared. So I skipped the partial part and did it mentally. we could clean stuff up, but now just plug in 2, 1, okay? equals, I don't know, and I'm not going to do it, but you get the idea? You just plug in 2 and 1 for x and you're done. All right, I'm going to move on if that's okay. Anyone still need this? Okay. All right. So this is really an important thing here. Notice that the formula that we had just a second ago, right? Come back to me. We had this formula for the directional derivative, a times partial of f with respect to x plus b times partial of f with respect to y. We could, if we wanted to, write it as a dot product of two vectors. Remember what the dot product of two vectors is, right? If I have two vectors, here's one vector, dotting it with another vector, then if I say dot, then you multiply the x components together, plus, and then you multiply the y components. If I choose my two vectors to be these two vectors, so I create this new vector, which the x component is the partial with respect to x, the y component is the partial with respect to y, and then that AB is that unit vector. If I dot those, right, then won't you get this? Wouldn't you get that formula right there? Now here's another notation for it. Instead of writing partial of f with respect to x at xy, partial of f with respect to y at xy, we cut out the xy. It's just understood it's at xy, and we just write f sub x, f sub y. Y'all still agree? So the directional derivative can be looked at as a dot product if we so desire to write it that way. Now, why is that an important thing? Well, we'll get to why it's important. We now define, okay, we are going to define what is called the gradient vector. The gradient vector is defined to be the two-dimensional vector where the first component is the partial with respect to x, and the second component is the partial with respect to y. Now, I want to take a step back to make sure we really understand this. If somebody gives you a function, right, f, a function of two variables, example of that would be f of x equals x squared plus 2xy. That is a function of two variables, right? We call this a scalar function because there's no vectors involved with it, right? It's just this times this plus this. It's just multiplication and addition, right? You plug in something, you get a number out. We call it a scalar function. But if someone gives me a scalar function f, I can create this thing called the gradient vector from it. And the gradient vector is simply just the partial of it with respect to x as the x component, and then the y component is the partial with respect to y. Create a vector. Now this little symbol in front of this f is our gradient symbol. That's actually called the del symbol. You've heard me use del before when we were using partial with respect, partial x with respect to t, something like that. We used that little like backwards 6 looking thing. I called it del. Del is a weird term that we use for both this and this because this del symbol means a partial, doesn't it? It means you're going to be taking partials. And so we use del for that also because it's a partial. It's kind of a weird thing. But we have del of f, okay, or the gradient of f is just that vector, which is this. Okay? So find the gradient vector of this. So you need appropriate notation here. The gradient of f equals the vector, right? What is the partial of that with respect to x? That's the first part. So what's the derivative of e to something? Itself, right? E to that something. Times the derivative, what's up there? What's the derivative of x times y with respect to x? Just y. So we should get a y out front, e to the xy, plus, well, actually it's not going to be plus because what's the derivative of cosine? Negative sine. So I have negative sine of x plus y, and then times the derivative of what's inside. What's the derivative of what's inside of this cosine with respect to x? 1. So I don't need to write anything else. That's the first component of the gradient vector. And then the second component is very similar, isn't it? It's just x e to the xy. Then the same thing, right? Minus sine x plus y. That's it. You don't have to change around what? You could go y plus x or x plus y. Whichever. All right. Now, everything we've done has been two-dimensional, but we can extend it all out to a function of 3 variables. So if we have a function of 3 variables, right, and you give me a unit vector, u is the vector ABC now, so 3 components, 3-dimensional, then the directional derivative in the direction of u is just a times the partial of f with respect to x plus b partial of f with respect to y plus c partial of f with respect to z, and you're done, right? But then you can also look at that gradient now as being those partials, right, in a three-dimensional vector. So this is just an extension of what we just did in 2D, right? Ugh. This doesn't look fun. All right, let's see. We're going to want to get the gradient vector. So I will start with some groundwork. To get the gradient vector, I am going to need some partials. So let's see if these are easy to get. What's the partial of f with respect to x here? What is it? 1 over y plus z. Y plus z on the bottom is like a constant. It comes out, and you just have x, right? Right. This is the same as writing 1 over y plus z times x. And then y and the z are constants, so that's 1 over a constant. So derivative of that with respect to x is 1 over y plus z. Now, what about the partial with respect to y? This time, you can't do that because y is in the denominator. You could use quotient rule. You want to use quotient rule? That's fine with me. I'll use quotient rule since it was mentioned. What would the derivative of the top be with respect to y? What's the derivative of x with respect to y? 0, because you're holding x as a constant. Oh, wait, are you doing low-D high, high-D low, or am I free to do this however I want? Okay, I do derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. That's what I've always done. It's basically the same as the product rule formula with a minus instead of a plus and squaring the bottom. That's all it is. So I do derivative of top, which is 0, times the bottom. It's not going to matter, right? Minus derivative of the bottom with respect to y. 1 times the top, x, all over the bottom squared, which just gives me a negative x on top, and then y plus z squared. Y'all see how that worked? That's your partial with respect to y. You mean like bring that up as a negative exponent? That was another option. Yeah. Yeah. Some of you probably realized in Cal 1 that you can oftentimes get rid of quotient rule and just do chain rule. Yeah. Okay, f, partial of f with respect to z. That's going to be pretty damn close to what we just got, right? What will it be? Same. Same thing. So not pretty damn close. Exactly what we just got. All right, so that just allows me to create the gradient vector, right? So the gradient of f is equal to 1 over y plus z, and then negative x over y plus z squared, and then negative x You know how he can't lay down or he dies? The last 2 days, I haven't been able to sleep laying down because if I do, I can't stop coughing. And I've been sitting up sleeping. All right. Really? Yeah. My dad has that too. All right. That's our gradient. So we've answered part A, right? Part B, we want the directional derivative at the point 411 in the direction of u equals 1, 2, 3. So can we use that direction vector? No. So again, I kind of try to trick you a little bit here. You first have to get a direction vector that works, which is that vector scaled by its own length. What is its length? Root 14. So that's our direction. So I'd write the direction vector, or the directional derivative in the direction of v at the point xy will be equal to what? Oh, thank you, xyz. I'm still in 2D here. What happened here? Oh. Z will be equal to, it's a times the partial with respect to x plus b times the partial with respect to y plus c times the partial with respect to z. So you're just going to put these, yeah, you're dotting them. Yeah, you know what? I like that notation. Let's write that down so that we're all aware of that. This is really just the gradient of f dotted with v, isn't it? That's what it means. Which is 1 over root 14 times 1 over y plus z, and then 2 over root 14 times that negative x over y plus z squared. And then the last component is the same exact thing, right? Oh, no, it's 3. Sorry, 3 on top. Do I need to actually go in and plug these numbers in? Or do you think you could do that yourself? Do you think you could plug in 411? Yeah, and get your answer though is going to be a what? Oh wait, hold on. This is all messed up. Get these out of here. Why did y'all let me dot that and come up with a vector? Damn it. You assume that I knew it since I'm up here and you're there. That's a good answer. Yeah. I could blame it on medication, but I'm not on medication. So I usually am. That's the thing. I'm usually medicated when I'm up here. Okay, so we take a dot product, so it's these two multiplied, add these two multiplied, add these two multiplied. Because that directional derivative, the answer should be a what? A number, right? And that number represents a rate of change. Now, what you might be thinking is, like when we were in two-dimensional space, the directional derivative, it was easy to kind of visualize it because you had the idea of standing on a surface, right? Pointing in a direction and saying as I walk in that direction, I either go up or down, right? But what does this mean? I don't know. I have no idea what you're talking about. It was there the whole time. Getting back. Well, yeah, I mean, what we have here to start is a function of three variables, right? So you have three inputs. Agreed? Well, let me give you an example that actually would make some sort of sense, all right? Something that we can kind of wrap our heads around. Let's say that I'm standing in this room. I have a coordinate, an x, a y, z coordinate, right? Or let's say my hand is a point in this room. Then if I come over here, my hand is at a different point, right? And the temperature at this point is going to be different than temperature at this point, just slightly, right? And then maybe it's always changing, but let's just say, you know, there's temperature differential as I move through the room. Then let's say that this function, you plug in the x, the y, and z coordinate, and it spits out the temperature at that point, okay? Then I move over here, I have a different temperature, and over here I have a different temperature. Then what does the directional derivative represent? The directional derivative tells me then that if I'm sitting here at some point in three-dimensional space, and you give me a unit vector that gives me a direction, okay, to point in. Once I have that unit vector to point in, as I start to move in that direction, the directional derivative will give me the what then? The rate of change of temperature. The rate at which the temperature is changing as I move in that direction. So that is something I think you can kind of wrap your head around a little bit better. You know, temperature. That's always a classic example whenever you have three-dimensional space, you know, or three variables being plugged in, and then a fourth one number coming out. So a function of three variables is what I'm trying to say. You can always use space and temperature. All right, copy this real quick. Oh yeah, yeah. You can have 4, 5, 6. So, you know, let's say that. I mean, there's so many things that you could come up with, but trying to think. I mean, like if you watch the Olympics, right? If you saw any of them, you all know that the Olympics just were on, right? Hopefully, for the last 2 weeks. Think about just like someone skiing down a hill, right? And just their speed on the skis. Think about how many variables are in play there, right? You have all sorts of things. Coefficient of friction with the skis, you got wind, you got humidity, you got pressure, you got all these things. Imagine you take all of those and you determine, maybe there's 8 variables, and you use that to come up with a function that models the speed. Then your directional derivative would somehow give you your rate of change of speed, instantaneous rate of change of speed in a direction. So I mean, it doesn't matter how many variables. This will always represent the same thing. All right, got to get going here. All right, this is a huge note right here. Maximizing the directional derivative. So let's go back to the two-dimensional example again, okay? Because that's the one that makes most sense. If I'm standing here on a surface, I'm at a point, I can point in any direction, right? In every direction, I should have some rate of change. What I want to know is there an easy way for me to be standing at a point and say, oh yeah, point that direction, that's the maximum rate of change you're going to get? Or does that seem like it would be hard? Like you know the function, you know the surface, right? And I'm standing at a point, and I can go in any of 360 degrees And every angle in between, I mean, you know, I don't have to go 1 degree, 2, I mean, I can go any infinite number of angles in between 0 and 360. Do you think it'd be easy for me to just be like, oh, sure, point in that direction, and that you'll go up the steepest? Or doesn't that seem like it might be a challenge, though? I mean, I don't know. Okay, so it doesn't matter. This is the result. Remember back from earlier this semester when we defined a dot product, we said that the dot product can also be looked at as the magnitude of u times the magnitude of v times cosine of the angle between them. Agreed? But if we just said that the directional derivative can be looked at as a dot product of the gradient and the direction, then we can look at that gradient dotted with its direction as the magnitude of the gradient, which would be like what? Well, isn't the gradient, well, let's just keep going. I'll get to this. The magnitude of the gradient, right, times this, times the magnitude of u cosine theta. But what was the next one? Magnitude of u is gone because what's the magnitude of u? 1. Okay? The largest this can be is when cosine of theta is 1. Right? The magnitude of the gradient of f is a positive number. I mean, is 0 or positive. And then cosine theta, the biggest that can ever be is 1, right? So the largest that this dot can be, the largest that this dot can ever be, is when the angle is 0. Agreed? The what angle, though? The angle between the what and the what? The gradient and the direction you're pointing. So what you have to try and get your head around this. You go up on a surface. You're standing there, right? Now, this function f sitting over here has a gradient, regardless of where I am on the surface, right? Has a gradient. It's the vector that comes from the partials. So I get up on the surface, I'm standing, I'm like, which way am I going to point? Well, it turns out that all you have to do is take that gradient at that point, and that's a vector, right? Point in that direction, and that's your maximum, always. So the angle, you're saying the angle between where you need to point, where I need to point, so the gradient's like over here, I say my angle between that has to be 0, so I have to be pointing in the direction of the gradient. That's it. Now, do I have that written? Yeah. That's what I say at the end here. So that's the summary. The maximum value of the directional derivative is the magnitude of the gradient and occurs when we point in the direction of the gradient. That's big time. So here's an example. If f of xy equals sine x minus y plus cosine x, then find the direction as an angle of the maximum rate of change at 0, 0. Well, what angle gives us the maximum rate of change? What angle? Well, that's why I want to make sure y'all aren't confused. 0, the angle 0 is the angle between the gradient and which way we're facing. So the result of the previous note says, if you want to go maximum change, you always point in the direction of the gradient. You don't point always in the direction of 0. You always point in direction of the gradient. So if I want to say where's the maximum rate of change going to occur, all you have to do is tell me the angle of the direction of the gradient. So let's find the gradient vector and then find out what angle it's pointed in. So what's the gradient of f here? What's derivative of sine of x minus y with respect to x? Cosine x minus y? Anything coming out from the inside? No? Okay, plus what's derivative of cosine x? Negative sine x. Okay, the next part of the gradient is the partial with respect to y. So this time I get negative cosine x minus y. because chain rule popped a negative out from the inside, and then nothing else because derivative of cosine x is a constant, right? I mean, it's 0 because it's a constant. That's the gradient of f. Now what I need to do is plug in where I am. So I'm going to say the gradient f, and then look, I mean, there's so many different ways to notate this. You could put underneath here at 0, 0, so everyone knows you're plugging in 0, 0, or you can put it out in front. Okay, I just am letting you know I'm plugging 0, 0 into this. What is it? Well, what's cosine 0? 1? What's sine 0? Okay, over there, 0 again, cosine 0 is 1? 1, 1? Negative 1, thank you. 1, negative 1. So let's try and summarize again. If I'm standing here on this surface, the surface sine x minus y plus cosine x, if I'm standing up on the surface, and below me is the origin, right? 0, 0, the origin in the domain. What this is saying is if I want to point in the direction of maximum rate of change, I need to point in the direction of the gradient. And so I need to point, what, 1, negative 1? Where's that? 1's that way, right? Negative 1's that way. So 1 and 1, I need to be pointing that way like this. Now what's that angle? This is x and this is y. 1 that way. That's the vector, right? That's the gradient right there. At 0, 0. And that angle, we have to come all the way around. It's 315 degrees. You could say negative 45. You say negative pi over 4. It doesn't matter. So the angle would be negative pi over 4 is fine. That's the answer to part A. Now that's the angle I would need to point, okay? That's where I need to point. Now what is the maximum rate of change? So if I now take a step out in that direction, what's my rate of change going to be? So what did the note here before say? Let me remind you. The magnitude of the gradient is the maximum value of the directional derivative is the magnitude of the gradient. The direction is the gradient itself, but you take its magnitude, and that's the maximum rate of change. So for part B, all I have to do is take the magnitude of the gradient at 0, 0, right? Which is square root of 2. And that's it. What I can't really tell you right now, though, is whether or not it's going up or down. Right? Am I going to be going up or down? That's not determined here. But what I can tell you is that it's the maximum rate of change. So imagine there's two ways to look at it. If I'm pointing in this direction, right, and we say that's maximum rate of change, it's going to be square root of 2. Well, let's say it's going down, right, like that. Then what if I turn 180 degrees and go that way now? What is it? It's positive, though, right? So it just depends on which way you're pointing. It's root 2 is the maximum rate of change. Doesn't really matter if it's positive or negative. All right, that's a pretty good result. Next. Do we want to do this? No? That's good exercise for you? Is there anything special here? You would need the gradient, right? What's the gradient? Ooh, the gradient's easy, isn't it? 2x, and then that's the x component, and then the y component is, or I'm sorry, x. We say 2. X, and then y, negative y. But this is too easy. I'll just do it. I mean, it's just, I think it's too easy. I have to. I could have finished it if I just would have done it to begin with, right? The gradient of f is x negative y, isn't it? And the gradient of f at the point 1, 2 is 1, negative 2. And we go ahead, we can get the magnitude for part B. Okay, well, this makes it a little interesting. If we go to the right 1 and go down 2, right? That's our gradient of f at 1, 2, or 1, negative 2. Okay, so the interesting part is you have to recover the angle here. But you can just do a right triangle. This side's 2, this side's 1. To get angle, you could use what? Arctan? Arctan of 2. Someone on their calculator in degree mode real quick, arctan 2. So theta equals arctan 2. What is it? 63 degrees, but it thinks we're in a different quadrant, so it'll be negative 63 degrees. 63 degrees on your calculator, but scratch that. It's actually negative 63. Right? The calculator doesn't know we're in the fourth quadrant. You could have put a negative 2 in there, and it would have helped. But you still should be comfortable enough with right triangles to get that angle. So part A is answered. Part B is the magnitude of that vector, wasn't it? Magnitude of the gradient, which is root 5. That would be more of like an in-class test. Yeah. But, I mean, yeah, that, see, what I'd like to do is think about a test problem. Do you think that I would ask you problems about taking partial derivatives, like in the section about partial derivatives? Probably not, because I can just ask you a gradient problem, and there you have to show me partial derivatives. And as you'll see in 11.7, I can just give you one problem in 11.7, and you've got to be able to do all of it. So, you know. I don't know. I haven't made it yet. Let me see. What am I doing? Taking a picture. So you're saying you want me to push you? Is that what you're saying? Ah. All right. Let's look at this real quick. I want to read through this first, answer part C before we do anything. Let f of x, y, z be equal to x sine y, z, then find. So now I've automatically gone into a function of 3 variables now, but everything's still the same, okay? Everything extends out. So the first thing is I want the directional derivative at 1, 3, 0 in the direction of the vector 1, 2, negative 1. Then I want the magnitude of the gradient at 1, 3, 0. Which one of those do you think should be bigger? A or B? Go back to the surface problem where we had, when we were a function of 2 variables. We said you're on a surface, right? Directional derivative was the rate of change. You just have to give me which way to point. I'll take a step out. It'll tell me my rate of change. That's the directional derivative. The gradient vector is the direction that I point in to get the largest rate of change, right? And the magnitude of it is that largest rate of change. Which one should be larger then? B. Unless what? Unless the V up there is the gradient vector or a multiple of it. It would have to be unit length. So, okay. So it should be B. Now let's just compute it real quick. But that doesn't seem like it's going to be real quick. But we'll go for it. Let's work first on getting our, you want to do the gradient first? Let's do gradient. What is the partial of f with respect to x? Sine yz. What's the partial of f with respect to y? So x is like a constant. What's the derivative of sine of something? Cosine of it. What's the derivative of yz with respect to y? Z. So that z is going to come out with the x. And then do the partial with respect to z. It'll be xy cosine yz. That's a vector because it's the gradient. I need my directional my u, right? I need my direction I want to put. I'm doing part A right now, so I need my direction. What's my direction? Well, it's some vector u, which has to be unit length. So I have to take that v vector and scale it by its own length. 1 over root what? 6? Root 6. What? Yeah. Join the club. That's a vector, right? So the directional derivative in the direction of u at xy is basically the gradient dotted with our u, which is not a vector, Robert. Sine yz over root 6 plus xz cosine yz over root 6 plus xy cosine yz. Do y'all follow all this? Anyone have a question? Pardon me? Oh, negative, yes. And the second one should have it too. It was there. I don't know what you're talking about. Yeah, the 2 here, and then the negative. I make those mistakes on purpose, see if you're paying attention. I'm just kidding. I make mistakes. I'm human. Now we want to know what's happening at what? 130? All we really need from that, well, we need them all because we have z here. So someone, why didn't y'all catch my z here? Oh, you did? It's there. You can't see it. I'm having a good Monday here for sure. I need a picture of this so I can move on. But is it an easy plug-in? Come on, is it easy? It is? Oh, because we get 0 here. Sine of 0, 0, great. Get 0 there. And get 3. So is it 3 or negative 3? Is it negative 3? So that whole thing comes out to be negative 3? Over root 6. Okay. Awesome. Go ahead. What? Sure. Yes. I mean, it's really up to you. I mean, it wouldn't be wrong. It'd be perfectly fine. Yeah. So at 130, we get negative 3 according to the class, right? Over root 6. Oh man, what a day. And we still have a ways to go, 35 minutes. Negative 3 over root 6. All right. Picture. And I'm going to move on. Because now what I'd like to do, well, maybe I won't move on because I need some of this, don't I? Yeah, instead, let me just erase some of this. For part B, I still need the, what do I still need for part B? I need the gradient, don't I? And then I need its magnitude. So right now for part B, I'm just going to scratch out A and put, I want the gradient at 1, 3, 0, which should be what? 0, 0 again. It was 0, 0, right? Same thing. But now, what's there? That last one? 3? 3. What does that represent? What is that in terms of this problem? It's the direction I should point in for the largest rate of change of f. Now, what is the largest rate of change? The magnitude of that, which is 3. That's bigger than negative 3 over root 6. So no matter what vector you ever pick, any direction you want to point in, you'll never be able to exceed that you'll never be able to exceed 3 in terms of an absolute value of the slope of the tangent line. All right, so let's take a look at this last problem here, or last topic. We discussed a while back equations of tangent planes. You might recall this. What I said last time was that if we had a surface, okay, I'm writing this on the side. If we had a surface, z is equal to f of x, y, we could find the tangent plane by doing what? It was like, yeah, the normal vector, that A, B, C part came from the partials. Look back in your notes. In fact, since I give you your notes, I'll tell you what the hell I'm talking about. This was in the section on partial derivatives. Is it 11.4? Yeah, 11.4. So I'm referring to the formula 11.4.1. If you go back and look at that formula, you'll notice that the normal vector, which is usually A, B, C, A is the partial with respect to x, B was the partial with respect to y, and the thing in this formula, in this section, 11.4, was that the C, the one in front of the Z, was always negative 1. That's different than what we're seeing here. Okay, so I don't want you to mix the two up. But the main thing is we no longer need to have something that looks like z equals f of x, y. We no longer have to be able to solve for z in terms of x and y. You can have any equation where you have 3 variables x, y, and z equals some constant. We did a lot of things. Remember that section on quadratic surfaces? Right? Ellipsoid, parabolic, all these paraboloids, the hyperboloids, two sheets, all those things. Those are all equations with x, y, and z in them, sometimes missing different variables, but they're equations where maybe sometimes it would be difficult to solve for z and get it to look like that top right. Well, fear not. This is a more general way to get a tangent plane on any equation containing three variables. And it looks really similar, doesn't it? I mean, I know it looks like crazy chaos up there, but it does look similar because we still have the x naught minus y naught, the y minus y naught, z minus z naught. These things in front, those are our a, b, and c, aren't they? Those are the same. As far as a, a, b, and c, the a is still the partial with respect to x. The b is still the partial with respect to y. The c is now the partial with respect to z. But what capital F is no longer what it was over here. F was our function of x and y. Over here, F is the left side of the equation. Okay? You get your constants on the right side, everything else on the left side. That's the left side would be your f of x, y, z. So what's the normal vector of this plane? What's the normal vector? It's this, right? A, B, C. But that's just the gradient, isn't it? It's just the gradient vector. So the gradient vector is the normal vector of the plane in this case. And that will allow us to do this example. And then we're going to be done with 11.6. And that's exciting. Find the equation of the tangent plane to the ellipsoid. X squared over 9 plus y squared plus z squared over 25 equals 18 at the point negative 3, 4, 5. So you have an ellipsoid, looks like a big egg, right? You want to go to some point on that egg and then imagine a tangent plane being slapped onto it. What is the equation of that tangent plane? So according to the last thing that we just put up, we need the gradient of something, don't we? But what is it that we need the gradient of? Capital F, right? What's capital F here? It's the left side of the equation. Because I have the left side of the equation equals a constant, don't I? If it was not equals a constant, you would have to move things around until you got it there. So let's do the gradient of capital F here. The gradient should be the partial of that capital F with respect to x, which is 2/9 x. Partial of capital F with respect to y. 2y. Partial of capital F with respect to z. 2/25 z. All right. That's our gradient. Now what I need is the gradient at that point. What's the gradient at the point negative 3, 4, 5? So what happens if you plug negative 3 in for x? You get negative 2/3. What if you plug in 4 for y? 8. What if you plug in 5 for z? 2/5. What is this vector? It's the normal vector of the plane, right? So once you have the normal vector for a plane, all you need is a point on the plane, which we have. So the equation is negative 2/3 x minus x naught, which would be x plus 3, plus 8 times y minus y naught, which would be y minus 4, plus 2/5 z minus z naught, which would be minus 5, equals 0. Don't do anything with the what? 18. Oh, yeah. Oh, the 18 has nothing to do with it. I always like you to distribute through, but whatever. Whenever I have something like that, I just do like an LCD and just clear out all the fractions. Because the right side's 0, right? So you can just multiply by, let's say, 15 and get rid of all fractions, and then just work it out. But I guess for now, that's good. Questions? Comments? Concerns? I'm going to move on. Yes. Yes. Here, and here. That's your x naught, y naught, z naught equation of a plane. Yes, just like we always have. If we're given a point, we plug into the formula for the plane, right? I'm out of room. That's the equation of a plane. It always has minuses in there. So whatever you put in there, it's going to be really like the opposite of the sign. All right, I'm moving on. I think I have a visual of what we just did. So there's the ellipsoid, and that point on the ellipsoid is there, right? That's the point, and we found the plane. A lot of times when I work problems like this, it's the first time I've ever worked them or something, I'll have the computer draw this stuff for me and see if my answer looks right, you know? And that kind of verifies that we did find the tangent plane, right? That plane looks like it goes through that point, and it looks pretty darn tangent. Okay. Do you see that you couldn't really do this problem as an f of xy? Because this isn't really like a surface. This is kind of like a circle used to violate the vertical line test, and an ellipsoid kind of violates the vertical line test for a function in three-dimensional space. So, but we can still find tangent planes, which is nice. Well, we have, I mean, just anytime you want to find, like maybe where you have, I don't know if you've ever seen like optimizing packing problems where you have weird shaped objects and you're going to pack them, you want to find like an optimum way to pack them so you get the most in, then you want to find where their points of contact would be, and that would be basically where you'd have tangents hitting each other. Tangent planes on weird surfaces, things other than ellipsoids. But I think one of what was the problem? I can't remember what it was. Damn it. Was it Skittles or M&Ms or something? They were trying to figure out. I don't think it was Skittles and M&Ms though. It was something where they were trying to find the optimum way to pack some objects. They weren't perfect spheres. There was something else, and they were saying, we're going to put a bunch of them onto the back of a truck and take them across the country. We want to get as many as we can on that, right? We're fixed in certain dimensions. How do you pack them? You just throw them all in there, right? You organize them a certain way, then you get more on there. Skittles. Anytime you have a function of three, well, an equation containing three variables. If it was a function of two variables, like z equals f, then we could use the other one. This one kind of allows us to get around that and not have to have the function qualification. So yes, quadratic surfaces would be, this would be the way to go. Now, number 9 is example 9, I thought we were done. It's just a slight little change on this. We have never talked about what's called a normal line. But imagine you have a plane. We already talked about all planes have a normal vector, right? That vector just slides around. A normal line to a plane is a line that's parallel to the normal vector coming out of the plane, so going forever, both directions, and passing through some point on the plane. So remember, what do we need for the vector equation of a line? Point and a direction, right? The normal gives us our direction. All we need is a what? A point. So in this problem, it says, find the equation of the normal line to the tangent plane of the ellipsoid. Well, we already did all the work. We already got the plane, didn't we? So the only information I need from, for example 9, is I get it from example 8. So I need I want R of t equals R naught plus TV, right? What about R naught? I can just get that negative 3, 4, 5, right? That's a point on the line because it's a point that's on the plane, and it's actually on the ellipsoid. And then what about my direction vector, V? That's just the gradient vector at that point, which was the normal of the plane, which was something 8, was it 2/3, negative 2/3? Negative 2/3, what? 2/5. All right. And so, I mean, just put those together and I've got my vector equation, right? Shit. This sucks. Here we go. And it's about to be gone. 3, 2, 1. This is just a picture of it. That's that same normal, that same tangent plane, but now there's my normal line, that blue line going right through the normal, right through that point. Parallel to normal vector. But that normal vector is coming off the plane that's tangent. It'll be orthogonal to the tangent plane, yes. At that point, the plane is a tangent plane. So the normal is orthogonal to the tangent plane. You can't say orthogonal to the ellipsoid necessarily because the ellipsoid isn't a plane. All right, now I think that page number is probably wrong. But it's just do the homework out of 11.6. I'll get you the right page number here. Yep, 667. Well, you have that down, right? So 667 is the page. Let's see. All right, so I want to start 11.7 because there's some stuff in the beginning of 11.7 that goes back to Cal 1. So I want to make sure that you're okay on this stuff. So let me see. This came up in the exam, the last one. You were having to find the maximum of a function. And a lot of you were like, well, how do I find the maximum function? I said, well, go back to Cal 1. How do you find maximums of functions? So recall from Cal 1, let's say you're given a function on a closed interval. How do we find what's called the absolute max and min of the function? I'm being real loose with things here because there's certain conditions that we needed, continuous differentiable function, but we're just going to assume you're playing with a well-behaved function here, all right? So how do we do it on a closed interval? Anyone remember how you do it on a closed interval? It's different than how you do it if it's not closed. Find the critical numbers and the endpoints, right? So what are the critical numbers of a function? Where the derivative is 0 or does not exist. So what you do is you take your function, take its derivative, find when it's 0, find when it doesn't exist. You take those numbers, you take the endpoints of the interval, and you take them and plug them into the original function. You compare them. The biggest is where your max is, the lowest is where your min is. Yep, 4.1, 4.3 is where it should be. Yep. So let's do a quick example of this. Let's say I have f of x equals 4x cubed minus 10x squared plus x minus 1 on the interval -10, 7. What's the maximum and minimum value of this function on that interval? And we say absolute maximum because what we're saying is that if you have a continuous function on a closed interval, then it must attain an absolute maximum and an absolute minimum on that interval. So a point that no other point is higher than that one, and a point that no other point is lower. Absolute maximum. So what's our first derivative here? 12x squared minus 20x plus 1. Okay. Now, critical numbers. Set it to 0. Well, quadratic formula, right? If you take that quadratic, set it to 0, or you just get on your calculator and use the solve feature. I really don't care what you do. You can solve a quadratic on your calculator. I'm okay with that. So do it for me. Unless I beat you to it with the quadratic formula here. Anyone know how to use the solve feature? Oh, you have that fancy calculator. Y'all know how to use your solve feature, or graphing, or however you graph it and find your... So what did you get? 0.05 and what? 1.61. Now, this is something I already noticed on some of the take-home stuff, is that as soon as people got the critical numbers, they automatically said, that's where the maximum is, without ever actually checking anything. You've got to check these things. So if those are the only two answers, okay, if they are, and I would love for someone else to agree with those answers, and what I'm going to do is I'm going to now take those two answers and the two endpoints and plug them into the original function. I'll do the endpoints here, then I'll do f of 0.05, f of 1.6, 1, and we get some answers. Now, I could also back this up with a graph, couldn't I? If I really wanted to. So if you have your graphing calculator, you could try this too. Can someone read off the function for me again? What did I give you? The original one, what was it? No, the original function. 4x cubed minus 10x squared plus x minus 1. But I gave you an interval of -10 to 7. I'm using WinPlot. Has anyone ever used WinPlot before? WinPlot? It's free. It's pretty nice. Okay, let me get all this crap off of here. There. This is WinPlot's answer. And I can zoom out a little bit here. It's not perfect, but I think it's obvious that the max and mins are going to occur where? At the endpoints. Okay, the min will happen at negative, what was it, 10, and the max will happen at 7. But what we're going to be doing, we have to be able to evaluate and do all that. You just saying, oh, and I looked at the graph, isn't going to work. You're going to have to take the derivatives and work them out. Okay? Go with me on that? Okay, so I won't plug in any more in that. I'll just leave it as is. I don't know why, but every time I try and minimize Mathematica and bring it back, my file's not there anymore. I can't find it. So I have to close it and reopen it. Now that's how you find the maximum and minimum on a closed interval, right? That's closed interval. So let's talk about open. Well, we got, 8 minutes left? I'm just going to put here max. No, wait, that was min, wasn't it? It was min there. This would be your min. This would be your max. Oh, is that 7? Okay. All right, so what about if it's not a closed interval? So what if you had something like, I don't know, continuous function on open interval, something like f of, I don't know, a equals, I don't know, a over, I don't know, 1 plus a squared? I don't know. That look familiar? That look familiar? That's the curvature of that one helix problem from the take-home test. And you were supposed to figure out the a that gave you the maximum curvature, which wound up meaning you need to find the maximum of that. And your restrictions were just that a had to be bigger than 0. So because of that, that's what I'm asking you to be able to do right now. The way you do it, you cannot use the previous thing. You can't just find endpoints, critical numbers, plug them in, compare them. What you have to do is first take the derivative. Find the critical number still. So when you take the derivative of this, you can use some quotient rule here, or if you like, chain. Derivative of top times the bottom minus derivative of the bottom times the top all over bottom squared, which should give you a 1, what is that, minus a squared on top, on the bottom 1 plus a squared squared. I saw a lot of people did this on the take-home test, and I'm happy if you even got to the curvature being that, but doing this is also correct. Now, is this ever undefined? Is the derivative ever undefined? No. In the previous problem that we just did a second ago, it was a quadratic, so that's always defined. But here, because we have a denominator, I look, okay, I don't have to worry about undefined at all, but I do need to figure out when the derivative is 0. The derivative is 0 when the numerator is 0. And setting that equal to 0, you get two answers. A equals plus or minus 1. Now, I did have a restriction, though. A had to be greater than 0, right? In the problem on earlier, A had to be greater than 0. So that meant that A must be what? 1. Now, from the few that I did look through, a lot of people took that and said, therefore, the maximum is at A equals 1. You have not proven yet that that's a maximum. It could be a minimum. Right? I mean, it could be. If you just look at the function, think about it, you can convince yourself otherwise. But that is something in Cal 1 that I take off big points for. If you just get to that, you still have not shown me what it is. So how do you determine if that's a max or min? Do you remember this? You look at the number line. Here's 1. Now we're looking between 0 and an infinity, right? And what we do is we pick two test points, that anything we want, and we plug two test points into the derivative. So I'm going to take 1/2, and I'm going to take 2. I'm going to take those test points and plug them into the derivative. What's f prime of 1/2? So plug 1/2 into the derivative here. Well, the top would be a positive number, wouldn't it? If I plug 1/2 in, top's positive, bottom's positive, so it's positive. This would be a positive number. What do I know if the derivative function is positive? That means the function's doing what? Going up. So over here, I'd like to draw an arrow saying f is going up. And then on the other side, if I plug in 2 into the derivative, I know that plug in 2, you get a negative on top and a positive on bottom. See a negative? That tells me that f is going down. So if f goes up and comes down, and at that point is a critical number where the derivative is 0, then it must be a local maximum. But in this case, it'll be the only maximum because the function continues to go down forever, so it can never come back up and have another max. So now you can say that the maximum of this function occurs at a equals 1. Now, just because we're doing this, what about a minimum value? Well, but look at the restriction, though. See, look at our restriction. A must be greater than 0. So what that really means is we're looking on the interval 0 to infinity. So you can't plug 0 into that function. If you could, your answer would be what? 0. So something's happening here. You're going up, you get to a maximum value, you come down, right? But no matter what, this thing has to be positive. So what I guess I'm trying to get at is there's two more things you should look at. If you were asking for minimum, I wasn't on the previous test, but if you were also asked for minimum here, you would need to look at these two things. What's the limit as a approaches 0 of a over 1 plus a squared? And then you would have to look at the limit as a approaches infinity is a over 1 plus a squared. Now, both of these are L'Hopital rules. Oh, wait, no. The first one is 0, isn't it? Plug in 0, you get 0. The second one is what? L'Hopital. Infinity over infinity. Take the derivative first time, you get what? What did I say? You wouldn't have to use L'Hopital here? Hold on, y'all time out. Hold on. A over 1 plus a squared. If I let a go to infinity, you have infinity over infinity. That doesn't matter. I mean, yes, but infinity squared is not different than infinity as far as the concept of infinity. That's just a dangerous way of looking at it. That's all I'm saying. Infinity squared. What's infinity squared minus infinity? Is that always going to be infinity? You could divide by a squared at the bottom, or you could use L'Hopital's rule. That's all I'm saying. I mean, Don't avoid it. I mean, in this case, yes, if you want to say infinity squared is bigger than infinity, yeah, but that's a tough, that's, you get into some, top and bottom were tied on infinities. So who would win this? No, who would win this? If x goes to infinity, who wins that? Why? Why? Okay. So what about x to the x squared? No, I'm just saying, I mean, like, then the top wins? I mean, at some point, though, here, you've got to have a method. That's all I'm getting at. Is just, it's dangerous when you make an assumption that, okay, it looks bigger because I think it's bigger. It's just dangerous. You have trying to think of one that you can't even do. I mean, who would win that one? Is n factorial bigger than n? So the top would win. But what if I do on the top like 1 minus? You know what I'm saying? I mean, you've got to have. I'm going over time here. You're right. Just make sure you have a way of doing it, though. That's all. That's all I'm saying. Have a way. My way of that first one would just be L'Hopital, right? Would be that. Limit, blah, blah, blah. That would go what, 0? So it would approach 0, yes. That's still, I'm not disagreeing with you. I just want to make sure we're careful. And if that was under a square root, that wouldn't have worked, right? Like if that was in, because then the square root undoes the squared, so to speak. All right, as long as you're all comfortable with that. Okay. I think that's exactly perfectly where I wanted to end it. Okay, because when we pick up next class, we'll start looking at trying to find the maximums and minimums of surfaces. So instead of looking at like a 2D function, look at a surface, figure out where all its highest and lowest points are. And that may sound easy. It's going to be it's going to require quite a bit of work. Have a good day. I'll be right there. Let me just turn off this video. Review.